there are two types of people that were invited for this conference. One who are old friends, and other people who are we want to collaborate with. I think Roberto falls into both of them. Let me note he said that I only fall into one of those, right? But that's fine. So.
Okay, thank you all for being here. As you can see, there's a slight change in the schedule, which also means that, well, it was a bit of a last-minute thing, or maybe last 10 minutes thing. So it means also that I didn't prepare my talk very carefully, but hopefully you'll bear with me. And I'll try to stick to the basics of what I have to say. And the theme of the talk, well, the title of the talk is the lower tail of random quadratic forms. So let's first define the kind of object that we'll be studying. Well, you have random vectors. Well, let me assume they are ID, just for simplicity, though we probably don't need that. In p-dimensional space, so this dimension, maybe even. And this is our sample size. And can you all read this? Is this too small or? Okay. And the object we want to understand is this random matrix here. Well, it's the average of xi transpose. And so, I mean, depending on the setting, you'd probably call this a covariance matrix, an empirical covariance matrix, or a design matrix if you're talking about linear regression. And so, I mean, the problem we're interested in is, well, this matrix has an expectation. And the easiest way to define the expectation is just to think about the entry-wise expectation of these matrices over here. And since they are IID, they're all the same. So this is just the expectation of x1 transpose, right? So if the vectors have mean 0, this would be their covariance matrix. And the general kind of question that interests us is how close these two matrices are. Though, I mean, in the end, I'm only going to be talking about lower bounds in some sense for this random matrix, right? But it is it's a general problem, kind of a problem that has been very well studied. And let me stay here. Problem number 1, which is not our main interest here, is find conditions under which you have the following thing. So for all vectors in RP, if you look at V transpose sigma hat V, it's sandwiched between V transpose sigma V and V transpose sigma V. Well, plus or minus, times 1 plus or minus epsilon, right? So you want to find conditions under which this holds with high probability. And, well, there's not such an easy problem. I mean, it's an easy problem asymptotically if you just fix p and let n go to infinity. Then because we have the law of large numbers, and say for the entries of this matrix, then everything works very well in the limit. And if you want to make this slightly more quantitative, you have central limit theorems that tell you how this fluctuates around its mean. But we're really interested in a non-asymptotic setting. So in principle, you want to consider n and p that are arbitrary. Well, you need some sort of restriction, right? Because you, at the very least, you want n to be at least as large as p. Otherwise, well, what the rank of this matrix at most n, right? So we need some sort of condition, but we want a quantitative result that in principle applies to any finite p and n that satisfies certain inequalities, right? And so this sort of results actually, I mean, there's one case in which this is simple, which is a case when these vectors are either Gaussian or what's called sub-Gaussian. But let's stick with Gaussian. I mean, in that case, you can find so say if x, well, the random vectors are normal, let's say with mean 0 and covariance matrix sigma, then this is sort of easy in the sense that there are standard methods that give you the right answer. And it turns out that you need something like n larger than p divided by epsilon squared. Now, of course, Gaussian is too strong. I said that sub-Gaussian also works, but even the name sub-Gaussian suggests that sub-Gaussian things are sort of similar to Gaussian things. So the question is, can you make substantially different assumptions that still allow for this kind of result? Well, we now know that the answer is yes. And so let me, but this took a very long time to take place. So the results okay, reference. The results by a Dongshak et al. On the case of log concave random vectors, which should be somehow the second easiest case of this. So log concave random vectors, I mean, you can think, for instance, of vectors that are uniformly distributed over a convex body, and they have many nice concentration properties. You'd think that somehow it would be very easy to prove things in that setting as well, but it turns out that technically it's very complicated. And it's a major breakthrough in those guys, Dongshak, Litvak, Pajor, and Tomshak Yagaman managed to prove such a theorem. So that was only in 2010, even though the problem has been around for a while. And then, well, you have a series of other results. And recently, there's this paper by Mendelssohn and Pauris, where they managed to significantly weaken the assumptions under which you get results like this. And essentially, you need 8 plus epsilon moments on the 1D marginals of these vectors. So meaning, if you take such a vector and you look at a one-dimensional projection, you want that one-dimensional projection to have 8 plus epsilon moments. They're somehow uniformly bounded, no matter which direction you pick. And right, so it's and that, as I said, is a very recent result. And actually, you need a little bit more. I mean, there are seemingly very well-behaved cases in which this fails. So, for instance, if you take something like, let's say that you take x1 to be the product of two things. One is just a standard normal random variable, and v is a standard normal random vector. Right in p dimensions. So Verschining and Srivastava noted in another paper about covariance matrix estimation, they noted that this example, even though it's a very well-behaved kind of random vector, it has infinitely many moments, it's very nice, but still it's badly behaved from the perspective of having this property here. Because you can show that, well, the norm of sigma hat n, the operator norm, it's at least as large as something like log n p, or sorry, square root of log n p over n, or something like this. So there's no way you're going to get this kind of result, which is kind of what should be the natural goal. Because you get this extra term here just because amongst these vectors, well, the v's all tend to have norm p, right? So you get many copies of these. Oh, actually, you don't need this. You don't have the square root. It's just log n. So the v's all tend to have norm p. It's sharply concentrated. But there's going to be one vector in here for which this prefactor, this scalar, is going to be of size square root of log n with high probability. And so you get this lower bound just by looking, well, this operator norm is at least 1 over n, the maximum norm of psi I vi squared. Right? And which is the thing that I wrote before. It's log n p over n. So what I mean to make clear by these preliminary comments is that problem number 1 is somehow a subtle and difficult problem. And I mean, so difficult is a technical aspect of it, right? So saying it's subtle really means that, you know, there are things that are not entirely obvious at first sight that might result in this sort of behavior not being true. But we're going to be talking about a different problem, which is a one-sided version of this. And in this one-sided version, I just want the lower bound part. And, well, there's, of course, the question of why you'd want to have a one-sided version of this. For covariance matrix estimation is you really need two-sided inequalities. But it turns out there are many applications for which this is really the main thing, at least in terms of getting upper bounds. I mean, those of you who have been watching Alex's mini-course, you've already seen that when you do this analysis of even ordinary least squares, something like this matrix comes up. I mean, I made the point of mentioning that yesterday, right, for the students who were here last week. This matrix comes up, and what you really need for the analysis to go through is a lower bound. That's something we also discussed last week, for those of you who were here. And there are other sort of, even this high-dimensional setting that Alex is discussing, there is a mini-course, this is the most difficult bit. I mean, there are other things you need in order to make everything work. Actually, they're mentioned in my paper. I mean, the paper, the same title. But it turns out that the lower tail really is the the main thing. And so here's the result we're going to prove. I'm going to state it in a simplified form. Right, so the key assumption is the fourth moment assumption on the random vectors, or rather on their one-dimensional marginal. So if you might have noticed that when I write this, I assume implicitly that this vector has second moments, right? That if you take some, for instance, that the expectation of the norm squared is finite. Right, I mean, I need this in order for this to make sense. So I'm going to make a fourth moment assumption, and this assumption is over here. So I'm going to assume that for all vectors v, that the fourth moment of the unit product of x1 and v. And now let me just make sure that I get the notation right. Yeah. So my assumption is that this is less than a constant age V inner product sigma V. And this, well, 1/2. Right? So you can see very clearly that just from Jensen's inequality, it follows that this is lower bounded. Let me put this in parentheses over here, by the second moment. Right? So if you move this inside, you get a lower bound. So this is lower bounded by the second moment, which is just V transpose sigma V. Right? Let me maybe write this over here, that when you look, V sigma V is just the expectation of x1 V squared. And that's the kind of thing you do in basic probability classes when you learn about covariance matrices. So this is always the lower bound, and what I'm asking for here is that there's this finite constant, which I call age, such that for any vector, you have this upper bound, right? So this is not too far off from the second moment. And then, under this assumption, I have the following result. I have that the probability that for all vectors V in RP, V transpose sigma hat n V is larger than, okay, so now they're, okay, I'm going to write it like this. 1 minus epsilon V transpose V. This is larger than 1 minus delta if, and let me put the if here. If n is larger than, well, there's some funny looking quantities here. So, well, let's see what this gives us, right? So I said before that the nice result is when you're able to prove that P over epsilon squared, n being larger than P over epsilon squared, sort of, right, in order of magnitude, is enough to guarantee that you have such a thing. Well, I actually talked about the two-sided result, right? I said, well, if kind of the holy grail was to be able to prove that n larger than P divided by epsilon squared is enough to get such a result with large probability. And that's the kind of thing we have over here, right? So if you, let's say you think of P as very large, so you can take, say, this delta to be e to the minus P, and then this becomes a constant times P, times with another constant in front, divided by epsilon squared. Right? So if in this high dimensional setting, in which somehow the, right, this only becomes an interesting problem if P is large. So in this high dimensional setting, you can see that getting, using n of this order suffices to make this event a very high probability event. And so are there any questions about this? Is it clear what the theorem says? And I don't think I'll discuss the applications of this much. And so if you're interested in that, you can read the paper. I'm mostly going to focus on the way this thing here is proven and how this assumption comes in here, which is really the main attraction somehow. Right, so so we have our theorem. And I'll try to convince you that it's not entirely obvious how you prove such a theorem, just by giving you a sketch of what a simple proof would look like, except that the simple proof doesn't work. Right? So as surely the specialists in the audience know, and the students also know by now, when you when you want to control such a random quantity, right? Well, it's actually infinitely many random quantities here, right? For each v, you have a different random variable. And when you want to control such things, kind of the standard way to do it is it's to use some sort of chaining or union bound argument. And here, the union bound should really be the natural argument. What does this mean, right? So it would mean the following: that the kind of the standard. Of course, I mean there are variants of this that you could try and use. So part one would say show that it suffices to control V transpose sigma and V for a discrete set or finite. Of V's. Right, so for the students, this is what we did in the mini course. We showed, well, if you can show this is close to V inner product sigma V over a finite but potentially very large subset of the unit sphere, then you're good. Then you know that maybe, well, if you have very good control over this finite subset, when you move to the whole sphere, you lose a little bit, but not too much. You can control that, and so it's good for your purposes, right? And and then you show that V transpose sigma hat V is tightly concentrated for any given V. So the reason why you discretize the sphere, say, or the set of vectors, is that then you can try and find very good bounds for how close this is to its mean, or, I mean, in this case, we're interested in lower bounds, really. And once you find these bounds, you know that for any fixed vector V, this is very well behaved, and you hope that somehow the probability that something fails is so small that even when you add this probability over all V's that you consider, the sum of these probabilities will be small, right? So that's sort of the standard method. And I mean, you could try more complicated things with chaining for people who know what chaining is. But this is a method used, say, in the Mendelssohn-Paoris paper, except that they do something that ends up being much more complicated because, well, in order to get the fine control they need under weak moment assumptions, they need to work harder. Right. So as it turns out, in our case, step number 2 is okay. Step number 1 fails miserably, or there's no obvious way to make it work. Let me first argue that step number 2 is fine. So what's the kind of random variable you're looking at when you fix V here, right? So let me remind you that sigma hat n, there's this thing here. Well, sorry. It's xi transpose. This means that when you look at this thing here, you have a sum of squares like this. So it's the sum of IID terms because the vectors xi are IID. And well, so the law of large numbers means that this should be close to its expectation if n is large, but we need a quantitative version of that. And luckily, we only need a quantitative version for this lower tail here. Right? So let me state a theorem that's or a lemma, whatever. That's going to come up later. I mean, the main point here is that we're in a very favorable situation in which we want to bound the lower tail of some random variables that are non-negative. So, I mean, it's really important that all of these random variables are larger than or equal to 0. So, let me write it like this. So, Zi, IID, non-negative random variables. And let's say they have with finite second moments. And actually, let me even be more specific here to have the kind of thing that we want. So let me say that if you look at the L2 norm, so you take the square root, this is less than age times the expectation, and this is finite. So age is really the same age that we got over there, as we're going to see in a couple of seconds. Then the probability that the sum of the average of the zi's is larger than 1 minus 2 log, 2 h log 1 over delta n times the, well, they're IID, right? So the expectation of the sum is just the expectation of the first term. Or the expectation of the mean, rather. This is less than delta. So let's see if this is clear. I'm taking the sum, and my hope is that somehow this is lower bounded by the expectation times a value that's very close to 1. And what I claim is that you can get that, and with this sort of sub-Gaussian probability, where, well, if you look at this ratio here, it's essentially 1 minus something which is like, well, there's this log 1 over delta divided by n, and you should, if, for instance, if you want to get this number to be like epsilon, what you need is to take n of the order of 1 over epsilon squared log 1 over delta. So this allows you to get even probabilities that are exponentially small in n if you fix epsilon. And so it's a very strong result. You certainly do not have that if you flip this to a less than or equal to and put a plus here, because here you allow for random variables that have very heavy tails. And when you have a sum random variables that have very heavy tails, I mean, you're very likely to get one term here that's just huge and completely kills any possibility of something like this being true. Okay? It's just because you're considering the lower tail and the random variables are non-negative that this works. So let's see how this applies to our problem. And so here we have the dilemma. So in our case, we take Zi to be in our setting, you take Zi to be xy inner product with v squared, which is certainly non-negative. This star inequality that we assume it is a consequence of A over there, right? So you have that the probability that V transpose sigma hat and V, which is just the average of these guys, the probability that this is larger than 1 minus 2h log 1 over minus delta n V transpose sigma V. The probability is less than delta. So the probability of a vector, this is wrong, right? So this should be greater than 1 minus delta. Okay, I feel better now. Right, I want to say that this holds with very large probability. And this should be also with large probability. Right? So it's saying that if you take any fixed vector v, this is very well behaved. Probability that this fails to be lower bounded by this times a constant close to 1 is extremely small. And this is exactly the kind of thing we need in step 2 of the standard method, which is show that for any fixed v, this is well behaved with very, very high probability. But then there's the issue of how you do step 1. And it was an issue that was in my mind for a while. And eventually happened to find the right technique, which comes from other people. It's essentially that when you try to move from a kind of, let's say, so you're saying, well, I take this, say, and to use the technical term, I take this epsilon net over the sphere, over the unit sphere in RP, and I know that V inner product sigma hat V is well behaved on this epsilon net. Now, when I say it's well behaved over all vectors, when you try to move that to do that, it seems that you need to control not only the smallest value of this, but also the largest value. And well, I mean, it's not clear whether what I'm saying is exactly right. Maybe there's another method that somehow circumvents that. But you do need to be careful. You remember that, as I pointed out, the assumptions you need to be able to control the upper tail of these random variables are stronger, strictly stronger than what I have over here, right? So it can't just be a matter of proving that the maximum is also well behaved. You have to do something else. And right? So what would be something else? And that's what we're going to talk about for the remaining minutes. Well, how many minutes? Maybe, I don't know, 20 minutes or something of my talk. So what we're going to see, what we need is a way to move from this sort of very good control of a single vector to the whole sphere, but a way that doesn't use any information about the spectral norm in this matrix or how the upper tail of this behaves, right? And the way I'm going to propose to address this issue is, I'm just going to put the name here. It's what some people call the packed Bayesian method. So apparently this name originated in the machine learning literature with this guy called McAllister. And 80, sorry, forget the year. And then there's John Langford and then Shaw Taylor in more recent paper from 2002. They devised a version of the method that's somehow closer to what we're going to see here. And the place where I really learned this as a paper by Oliveira and Catoni from 2014, is it? Or I think it's been published only in 2014. Oh, no, sorry. It's 2011 even. So it's you could say it's a slightly old paper by now in some sense. But it's perhaps I can claim to having derived an easier way to apply their method, but still remains a kind of a mysterious method for which is very good for some tasks, but it's not at all clear what its limitations are. It does seem to be very good. When you manage to make it works very well. But it's not clear when you can manage to make it work. Right? And before I apply this method, let me note something here, which is the following. So, I mean, the way you prove this lemma is actually going to turn out to be important for us. It's the way you prove this lemma here is you prove something which is called a kind of moment-generating function inequality, which I'm going to state in a form that's convenient for what I'm going to do later. So it's kind of, it's the lemma that lies behind this lemma here. And I'm going to state it just in the setting that we're going to use it. So, well, people who are familiar with concentration inequalities know that the standard way to prove such results is to look at moment-generating functions. So, because I'm interested in the lower tail of this thing, I'm going to compute the moment-generating function, or estimate it, at a negative value here. Right? And then, because you have a non-negative sum here, you have this result. You have that this is less than V sigma V plus age squared sigma psi squared over 2 V transpose V, V transpose sigma V squared. I'm just going to leave this lemma over here. And we'll take this to be our starting point in the following sense. That we're going to try to see how from such a result you can get the uniform control that we want over the lower tail. Right? And right, so what is this packed Bayesian method? So it's, in its essence, it's a different way to control an empirical process. So again, we have a family of random variables. In principle, it could be any family, but here's an exponential, well, it's an uncountable family of random variables. And, well, the standard method is you discretize the family and you apply the union bound. This method is something different. So it starts from something which is very, it's an inequality that comes from, well, it's an inequality about relative entropy. So if you know what those are, or about Kullback-Leibler divergence. So let's say you have two. You have a definition now. You have two probability measures on the same space. And, well, with, say, mu1 absolutely continuous with respect to mu0. And the Kullback-Leibler divergence between mu1 and mu0 is, by definition, the integral of your space. I'm not specifying the space here. 0, d mu1. Well, if you care about entropies, you can see that by writing this as d mu1 divided by d mu0 times d mu0, you have something that looks like entropy. And, but this is a definition. And let me just mention that if you have, say, two, if mu I is a Gaussian distribution with mean Vi and covariance matrix C, so the same C for the two, right? So here, thinking about two distributions over RP, say, which is the case that interests us. Then the Kullback-Leibler divergence is just, well, the inverse of C. Well, I'll take the 1 minus 1/2, actually. V1 minus V0 squared over 2. So for Gaussians with the same covariance, this is a well-behaved thing. Right, so what about this, right? Why does this matter? Well, there's a very curious result, which is comes from a variational characterization of the relative entropy, which is the following. So if you take any measurable function h on your space, well, it has to be integrable. So let's say, you could even assume it's bounded. Well, let me just put it here to avoid any sort of technical problem. You have the following thing. You have that the integral of h, d mu1, is less than a log of the integral of exponential of h, d mu0, plus the relative entropy. So the variation characterization that I mentioned is that the largest value of the difference of this and this is precisely this relative entropy here. Right. So why would you care about such things, right? It's so the general idea of the method is somehow the following. So let's say that you have, well, in a typical empirical process, you have something like this. You have a family of random variables indexed by some parameter, and the parameter might live in finite dimensions or in infinite dimensions. Well, it lives in some sort of measure space. Okay? And let's assume that you know that all these random variables have mean 0. And you want to control the supremum of these guys. Right? It's the kind of thing that we do in empirical process theory. Well, this is hard. As we know, this requires many different things. Well, we know kind of the optimal quantities to look at in the Gaussian case, but in another case, it's much more complicated, like this case here. Right, so what do you do? Well, what you do with this method is that you can look at these new random variables. I mean, you have to make some sort of measurability assumptions here. You can look at random variables that you don't look at the value of h sub n of theta for specific theta, but you average this over the measure mu1. So this is the definition. I'm just saying, well, mu1 of h hat n is this. So now you have a new empirical process, which is sort of funny and seems much less nicely behaved than this one. Well, the empirical process maps measures, well, probability measures over your space theta. Well, you need some sigma algebra. So it maps measures to random variables given by this formula. And again, you have to make some sort of assumption to ensure that everything here makes sense, but right? You need something, but in our scenario, this works well. And I mean, as I said, this empirical process looks more complicated than the previous one. Now your parameters are not in this parameter space, but probability measures. So how could this be any simpler, right? Well, what you have here is the following. So sup over mu1 absolutely continues with respect to mu0 of mu1 of h sub n is minus the Kubic-Leiber distance. Right? This maybe is the object that you care about, sort of, because this is not the original empirical process, and you have this other thing here as well. But this is less than something which is uniform. So now this is just a single random variable. Right? It's a funny random variable, but it is a single random variable. And if you want to, and what you're doing here, well, in order to control this, you need essentially to control the expectation of what's inside by Fabini's theorem. Well, I'm going to be more specific. But if you really want to talk about moment generating function, maybe insert a psi here, and you get this. Right? So it's a very funny method, but in the end, what it does is it translates something which is an empirical process into something which is a single random variable. And, well, of course, you need to be careful when you move from this to this, because what you really care about is this family here. So you want to choose your mu's in a way that sort of this smoothing out, right, this integral. Somehow, for each theta, you have a corresponding mu1 for which this integral is close in some sense to this. But let me give you an idea of how you apply this in our setting. So as I said, in the end, you're going to be looking at things like these. Right? So what are the key steps of the proof? So, and for the proof, I'm going to assume that this that the distribution we're looking at is isotropic, and I'm going to notice that because this is homogeneous in V, right? If you multiply V by a scalar, you preserve this inequality, right? And I just need to, I want V transpose sigma hat V greater than 1 minus epsilon for all V in the unit sphere. If I have this, then I have something with the norm of V squared here for all V, and because the covariance matrix is the identity, then fine, right? And I want this with high probability. Right? So what's the family of random variables that I'm going to look at? Well, it turns out they need to be slightly careful, but here's a family. So for us, theta is going to be a parameter in our P. And I'm going to define h sub n of theta, or actually I'm going to call it z sub n of theta, in a funny way, which has this psi in it. And the funny way will become clear later on. So you got psi norm of theta squared minus theta transpose sigma hat n theta plus psi squared h squared norm of theta to the 4 divided by 2. So this is a family of random variables. It's clear that if I can control this over all theta of norm 1, then I have something related to this, right? So if I know an upper bound for this over all theta of norm 1, then I have a lower bound for this guy. Right? But I mean, there's many technical things that I'm sort of skipping here, but that's the main point. Upper bounds for this mean lower bounds for this. Right, but you can't just use this process because what I said here, you really want to smoothen it out. So, and you see that you also need to pick a reference measure here. So yeah, it's always sort of upsetting when the very moment where you're going to prove the theorems when you erase it, but maybe you can remember this statement. Right? So, so I define this thing, which is related to what I want to prove. It has this funny term in here, which only makes sense now, I guess, right? So, okay, so a reference measure, mu0, is going to be a normal with mean 0 and covariance matrix, which is just the identity divided by P. Right? The other measures I want to consider are normals with mean V and the same covariance matrix. And we know that whenever, and I'm going to choose V of norm 1 here. Where I already mentioned what the Kullback-Leibler distance between two normals with the same covariance it is. You need to look at the inverse covariance matrix, so that's just going to be P times identity. Right, take the square root here, but anyway. So what you get is this thing here, right, for P over 2. And now you have to consider the smoothing, right? What's the effect of the smoothing here? So mu1, here I'm assuming I have mu1 depending on V, right? So maybe I should write mu V here. So what's mu V of the Zn hat theta? Well, what I have to do is to average over the choice of theta here. And because the mean, it's an average over a Gaussian distribution, so the mean is V, right? And you have to do the calculation, right? But what's going to come out to is because V has norm 1, you're going to get psi. You're going to get a minus V transpose sigma psi 1 minus this plus psi squared h squared 2. And then you get a bunch of other terms where you maybe get twice this. I don't remember. Okay, I'm going to say you get some constant here, and you get something which is like plus psi 1 minus trace sigma hat n divided by p. So it's actually nice, right? So this is the kind of thing that you want to upper bound because you want a lower bound on this. You get some extra term which has to be there somehow. And you get this other quantity which is just a scalar random variable, right? And because we assume that the mean of this matrix is the identity, so the mean of the trace is a trace of the mean, which is p. So this is something nice. This is the sum of IID terms will be mean 1, I was subtracting 1. So I expect this to be concentrated. Well, in the actual proof, you need to use some sort of truncation device to guarantee that this is very concentrated. But this is the least of our worries right now. And so what does this Peck-Bayesian inequality here say? It says that that if you look at the soup over V of norm 1 of this thing that I wrote over here, and then you have to subtract the Kullback-Leibler distance, which we saw is P over 2, right? So it's the same for all V's. This is going to be less than log of the integral of e to the zn hat theta d mu 0 theta. What about this, right? Well, this is a random variable. And you can compute its expectation, which, what's the expectation of an integral? Well, I forget it whether it's Fubini or Tonelli or whatever, but you can interchange these two. And here comes the trick. Well, the way I set things up guarantees that the expectation, well, there's no psi now, right? Because, yeah, that's right. The psi is already over here. I set things up so that the expectation of this quantity is always less than 1. And this might not be clear, but it's exactly this lemma over here. And this is for all theta. So no matter what you do here, this is going to have a random variable with mean 1. So the probability that this is larger than, say, e to the t is less than e to the minus t, just by Markov's inequality, right? So this is less than e to the t with prob greater than 1 minus e to the minus t. Well, you take the log, you get a t here. And in the end, what you have is, well, there's, yeah, that's right. So in the end, you have that something like 1 minus v at sigma n v is less than p plus t divided by psi plus some terms with psi squared, so which is going to become psi. And this, with high probability, you just optimize over psi, and you get a bound in the theorem. So modulo some technicalities and constants, this was really the full proof. And I'm already running over time, so thank you for your patience, and finish here.